You're good.
Okay.
So hi everyone. So I'm really happy today to have Ananda Suresh from Google to give us a talk. And today he's going to talk about communication efficient and differentially private stochastic gradient descent.
Hi everyone. Thanks for having me here. Thanks Salim for inviting me. Let me first share my slides and then I will start. Okay, can everyone see this?
Yes, yeah.
Yes.
Okay. So hi again. I'll be talking about communication efficient differentially private stochastic gradient descent. This is joint work with Naman Agarwal, Felix Yu, Sanjeev Kumar, and Brendan McMahon. All of us are at Google Research. Some of us in New York and some of us are in Seattle. This work is a culmination of two of our papers, one in ICML last year and one in NIPS this year. Before I go further, I should say that there were a lot more people involved in this project in terms of implementation and other research ideas. So if you're interested, feel free to reach out to me. Am I audible?
Yes, yes, everything is good.
Okay, cool. So let me start. So here is the outline of the talk. I'm going to first start with some motivation, in particular, what is distributed stochastic gradient descent? And then we are going to focus on a new paradigm, which we call federated learning. And then we are going to look at problem formulation, where we are going to reduce this problem of distributed stochastic gradient descent to that of distributed mean estimation. So it turns out mean estimation is a much easier problem to analyze, but the results for mean estimation directly applies to stochastic gradient descent. And for this problem, we are going to focus on two aspects. The first one is communication efficiency, and the second one is differential privacy. For communication efficiency, we are going to propose three schemes and show that one of them is minimax optimal. And for differential privacy, we are going to show that one can achieve privacy using binomial mechanism. So this is like a short talk, roughly around 45 minutes. So if you have any questions, feel free to stop me. I'm assuming people can stop me.
Yeah. If people have questions, they can unmute themselves and ask questions.
Okay, sounds good. So before, and also I have kept some parts of the talk as very basic because I wasn't sure how many people will be familiar with SGD, how many people will be familiar with differential privacy. So before we go further, let's ask ourselves what's new in distributed SGD. To understand that, we need to understand what do people usually mean by distributed SGD. Usually, whenever people talk about distributed learning, distributed stochastic gradient descent, they mean server-side algorithms. These are algorithms that are used to train your machine learning models faster and better. And it's at a very high level, it's a tool for computation efficiency. And this has several advantages because you are designing your network and you can buy whatever workers or components you want. So they are usually very efficient. And they have like top of the market, like the best GPUs and the best CPUs available. And something which is even more, which we take for granted, is that we can play God and design a network architecture, meaning what nodes talk to what nodes. And we can also decide how data is distributed among them. A typical example is, for example, usually people take the data set and divide it into k independent parts and distribute it across k data center, k workers. This is used for learning large-scale machine learning models, and it has been studied a lot in the literature in the last 15 to 20 years. However, our goal is slightly different, and we are interested in what is called client-based distributed SGD. Here, you have a central parameter server, which is the black box on top, and it wishes to learn a global model, let's say W, which can be a neural network, decision tree, logistic regression, whatever you want. And the data to learn this model is not located at the server, it's located across many devices. These devices can be cell phones, tablets, laptops, and I don't know what the last figure is supposed to be, but like let's say some gaming stations. It can be anything. And here, once we go to the second, whatever we took for granted in the server side of things doesn't hold anymore. So let's see what are the changes. First one, these phones or these clients are no longer computationally efficient. They may be good, but they don't have as much capability as like the best GPU that's available on the market. The second one, which is even more problematic, is that you cannot design a network architecture. You cannot say 10% of people should have brand one phones, 10% of people should use laptops, and so on. It's what's given to you. And again, for another example is data is not independent and identically distributed. You cannot say everyone has same type of data. Data that's used by people in US is different from the data you get from people in India. And if you train models, you actually notice patterns in your loss curves. Like in the morning, the loss behaves differently, but in the evening, the loss behaves differently. This is because of the time zone differences, and people who use these applications are different. And from a research perspective, it opens up several interesting questions. For example, since it's cell phones, now there are a lot of constrained resources. So for example, the memory is limited, the amount of bandwidth, meaning how much you can talk from the phone to the server, is limited, the power consumption in the phone is limited, and perhaps the most important of all of this is privacy, meaning you're actually learning on data which is there on users' phones, so you want to guarantee as much privacy as possible for the users. One of the classic examples of this setting is federated learning, which was introduced in a paper last year by Konoki et al. It's almost same as SGD, but there are some subtle differences, which is for this talk is not important. So is it clear? Okay, I guess so. So let me continue.
Yeah, everything is clear.
Okay, cool. Let me continue. So what are the challenges? Let's go over the challenges a bit more. So in the standard approach, each client sends a gradient to the server at each round of the stochastic gradient descent. Let's say your number of variables is D. Then to send the gradient to a constant accuracy, you need roughly D log D bits. This can be very expensive for large models with millions of parameters. Let's take a simple example. Suppose you're not a theoretician and you just want things to work. You would probably use something like the standard C++ or Python data structure implementations. So
what is D? Can you remind us what is D?
It is the number of variables in your model.
Okay.
Yeah. So if you have a D-dimensional vector, to represent it to a constant accuracy, you need D log D bits. Roughly. Okay. Yeah. And in a real life, like let's say you just care about implementation, usually people use 32 bits, like a float representation in C or C++. And the number of bits you send is 32 times D. Even so, let's not look at a production system, but let's look at a toy example. It's a language model for pen tree bank data set. People write papers on this all the time. This has 13 million parameters. So if you do the math, it turns out it's roughly 50 megabytes of data. And this can be very problematic. So the first focus of this work was how do you reduce this uplink communication cost? This is the communication cost from the phones to the server. And why uplink? Why not downlink? Because usually uplink communication is more expensive because you need to use higher power resources, and even the standard network operators provide you a smaller bandwidth for uplink than that for downlink. Typical number is like uplink would be like 5 megabytes, but downlink will be 50 megabytes. And second question we'll try to answer is what kind of privacy guarantees can we guarantee for the user? And we are going to, and the main topic of this talk is, can we do both of them? Like, can we guarantee low communication cost and can we guarantee privacy? So let me So this is the main motivation for the talk. I hope I have convinced you that this is a useful problem to look at, and it's actually one people encounter in practice. So before we go further, let's write a little bit more math. So in stochastic gradient descent, you have m functions. Let's call them f1, f2 up to fm. All of them are functions of some variable w. And this w is a d-dimensional vector. And the goal is to minimize the average loss, which is the average of these functions fi. The standard stochastic gradient descent algorithm works as follows. You first initialize w to some value w naught, and you repeat the following for t from 0 to capital T. First, the server selects randomly n clients, and these n clients compute the gradients of their local point, which is fi of wt. Let's denote it by gi. And these selected clients send their gradient to the server. The server takes the average of all the gradients it gets, and it updates the model by making a tiny move opposite to the direction of the gradient. More mathematically, the model at time t+1 is the model at time t minus some small learning rate times the gradient. This is standard stochastic gradient descent analysis.
Assumption here, how the data points are distributed on the clients?
The algorithm doesn't take into account how data points are distributed across the clients, but the guarantees usually assume that the data points are distributed independently across clients.
Okay.
And just to be clear, this is the usual way optimization folks write it, but fi of w will be the loss of your model w on the data points stored at client I. Does that make it more clear?
Yes, thank you.
Okay. So let's look at a sample result for an analysis of SGD. SGD has been analyzed separately for convex, strongly convex, and non-convex problems, but the flavor of them remains the same. Here I have taken an analysis, a result for non-convex optimization. This is from a recent paper, Ghadimi et al. What they say is, if the function is non-convex, under some assumptions, which are not important for this talk, the L2 norm of the gradient goes to 0 as the number of time steps go to infinity. And in particular, it goes as 1 over square root t. That's the rate of convergence. But for this talk, what we are interested in is the associated constant sigma. The sigma is the maximum variance of your gradients. If I take a step back, notice that each client computes its local gradient and sends them to the server. If the clients are selected randomly, then the gradient is this gradient is an unbiased estimate of the true gradient. So therefore, this sigma square is nothing but the mean square error in your estimate of the true gradient. So that's the one punchline I would like to convey from this slide. The SGD guarantees depend on the mean square error in the gradients. But perhaps, let's say you want to compress this vector for some reason, or you want to do some kind of post-processing. Let's say you compress the gradients from git to g tilde it, such that the g tilde is an unbiased estimate of the vector git. And let's say the server uses this process gradient g tilde, then a very similar result to that of Ghadimi et al. Holds, except sigma will be replaced by sigma tilde, which is given by the last equation on this slide. This is the mean square error of the new post-process gradients. So the takeaway is, if you have an SGD, the guarantee depends on the mean square error of the gradients. So when we look at this problem, we realize there's no particular reason we need to study this problem in its entirety. We just want to analyze how can we process gradients such that it's unbiased and you minimize the mean square error you incur in the post-processing. So this gives us the following very natural problem, which is mean estimation. You're given n vectors, x1 up to xn. These vectors lie on n different clients, and they all belong to a d-dimensional space. And the goal is to estimate the mean of these vectors. As in the previous slide, if you are interested in stochastic gradient descent, you'll set each xi to be the gradient of client I, and the server wants to recover their average. You can think of several other applications like power iteration for PCA or Lloyd's algorithm for k-means. In all these cases, it turns out the communication bottleneck is the one where you try to estimate the average of some vectors. So for the rest of this talk, we are going to just look at mean estimation. And the result for gradient descent follows from the previous slide, this slide, where the convergence rate will be 1 over square root t times the variance in your gradient estimate. Okay. So let me first, in the first part of the talk, I'm going to focus on communication efficiency. And in the second part, I'm going to look at differential privacy. Any questions so far?
No.
Okay, let me continue. So let's track the problem more carefully. So as I said before, you have n vectors and you want to compute their average. In this talk, we are going to focus mainly on non-interactive protocols, where at each time, where the client sends just one compressed vector q of xi to the server, and the server estimates the mean x bar by some function of these compressed vectors. We don't allow many rounds of communication. If pi is such a communication protocol and x bar hat is the estimated mean, the quantity we are interested in is the mean square error of our estimate, which is nothing but the expected L2 square loss. And we would like to achieve very small mean square error for a given communication cost. And now what's a communication cost? Let's say Ci be the expected number of bits sent by the ith client. Then we would like to minimize the total number of bits sent by all the clients, which is the sum of individual Ci's. You may notice that I have suddenly an expectation term in both the mean square error and the communication cost. But so far, I didn't talk about any probability distributions. In this talk, all the expectations is over the randomization in your communication protocol. And we do not make any assumptions about the underlying vectors x1 up to xn. And the goal is to understand what's the trade-off between the mean square error, is calligraphic E, and communication cost, which is calligraphic C. As I said before, we want to understand this for any set of vectors x1 up to xn. So to do that, we formulate the following minimax problem. Let's say BD be a unique Euclidean ball in D dimensions. And our goal is to evaluate this minimax mean square error, which is the worst performance of the best algorithm with a given communication cost. More formally, we have a communication budget C, and our goal is to find a protocol pi which has communication budget less than C, but minimizes the maximum loss over all possible sequences x1 up to xn. Okay. So when we formulated this question, the first thing was we were very surprised to find that this problem hasn't been studied so far. It's a very simple and very practical question, but surprisingly, it wasn't studied before. The closest work which we could find was a series of works on distributed statistical estimation. This is a line of work from John Ducci, Ankit Garg, Mark Braverman, and so on. But they look at this from a more statistical perspective. So for their problems, the vectors x1 and xn are usually generated IAD from some distribution. And usually it's either a Gaussian or a product of Bernoulli distributions. And the goal is not to estimate the empirical mean like us, but instead they want to find the parameter of this underlying distribution, like the original mean, the original variance, and so on. This is fine for proving lower bounds, but surprisingly, even their algorithms use the fact that their underlying distribution is Gaussian or Bernoulli. For example, here is an algorithm which they had proposed in one of the papers. They would like to estimate the mean of a Gaussian with unique variance, with as low communication budget as possible. So their algorithm was they first compute the error function, which is what's the probability that the Gaussian is bigger than 0 using samples. And then they output the mean for which the probability that xi is bigger than 0 is p hat. Notice that this algorithm works only for Gaussian distributions. It doesn't work in a minimax case, which I explained before. So to the best of our knowledge, ours is the first paper where we studied this problem without any distribution assumptions over the data, and we are interested in empirical mean. Around the same time as our paper, there was another paper by Alistair et al., where they used very similar techniques. The only difference was we used some version of arithmetic coding, but they used alias coding. Any questions so far?
Yeah, I have a question. So can you comment, because you started from the what you call the client-based SGD. So which one of these two models do you think it's would be a better fit for these types of applications? So meaning making these assumptions on the distribution, is this not a good assumption to make on these types of problems that you started by in the motivation?
That's a great question. So if it's very easy to evaluate this. Imagine you're running stochastic gradient descent. And since we are interested in the gradients, we can just plot their distribution empirically. And usually they do not satisfy any kind of distribution assumptions for both server-based and client-based.
So you're talking about real data. So you did this for real data?
It depends on what you mean by real. Even for like a toy data set like MNIST, it's like an image classification. Yeah. Even for that, they don't follow any probability assumptions.
Okay.
One of the main aspects is it varies over time, meaning the gradient depends on the point you're at. So that changes things a lot.
Okay.
Yeah, it's a very good question. Anything else?
No, I mean, from my side, no.
Okay, cool. Okay. So let me continue.
I have a question. Excuse me, sorry. I have a question. So I don't quite understand why you consider the worst case. Why you don't consider the distribution estimation case? Because in a real learning problem, you still need to assume the data is sampled IID from some distribution. Then you can have some learning error, or else it's just an optimization problem, right? So I don't quite understand why you consider the worst case setting in this problem. Why consider the distributed setting is enough? Distribution setting is enough?
The client-based distribution setting, the data set is not IID. Let me go over this. Yeah. In this picture, the data set is not IID.
Oh, I see.
Okay. And secondly, even when you assume data is IID, it's not like it's a Gaussian distribution, right? Imagine these are images which are shuffled across the workers. So it's not clear these images form some kind of Gaussian distribution. And the second step is it's not clear if the gradients with respect to these images again have some kind of Gaussian or Bernoulli distribution. I hope that answered your question. Next, yeah. So I'm going to talk about 3 protocols. The first one is a uniform quantization scheme. And again, this is like very simple textbook material. And then I'm going to vary it and improve it in 2 ways. The first one is stochastic rotated quantization, where we show how to use random matrices to to improve your accuracy considerably. And finally, I'm going to talk about some simple universal compression or variable length coding schemes, which we prove to show optimal communication mean square trade-off. So let's start with stochastic binary quantization. So recall that vector client I has a vector xi. So this is the algorithm which a particular client or a particular phone follows. Excuse me. It finds the minimum of all its coordinates. It finds the maximum of all of its coordinates. Let's call it xmin and xmax. And then it rounds off each value, each coordinate to either a minimum or a maximum with certain probability. A picture will make it very clear. Let's say xmin is the least value of all the coordinates. Xmax is the maximum. If xij lies in between, you move it to the minimum with probability proportional to the red part of this curve, and you move it to the maximum with the probability proportional to blue part of this curve. The advantage of this algorithm is that it gives a unbiased estimate of the underlying true probability, underlying true vector xij. And the server takes these quantized values and it just averages them. It's a very, very simple scheme. You first stochastically quantize each value to either minimum or maximum, and the server just takes the average of these vectors. Why is this a nice result? Why is this a nice algorithm? Because it has very, very low communication cost. So now notice that if you have a d-dimensional vector, if it wants to send the values, it has to first send the minimum value, maximum value, which takes roughly some order log d bits. And then for each coordinates in a vector, it just has to say whether it's minimum or maximum, which is only one of two values. So you need 1 bit. So the total communication cost for a particular client is d plus some log d factors. And the overall communication cost is number of clients n times d. And there are no hidden constants in the leading term. And you can compute the mean square error for this. It turns out it's very simple exercise. It turns out it's d divided by n times the average L2 square norm of your vectors. If you assume the average L2 square of the vectors is some constant, then this result essentially says if you send exactly d bits per client, the mean square error is d divided by n. Okay, and so this was our first algorithm which we came up with. It's nothing fancy, it's very simple. And a very, very natural way of improving it is instead of quantizing it to minimum or maximum, you quantize it to k levels. In particular, let's say you divide it into boundaries, b1, b2 up to bk. If xij lies between br and br plus 1, you again stochastically quantize it to br and br plus 1 based upon the red part of the curve and the blue part of the curve, such that you have an unbiased estimate. Now, what's the communication cost? Again, you need to send a minimum and maximum that takes order 1 bits or order log d bits. But now for each coordinate, you have to say which one of the k quantized values it takes. So you need log k to base 2 bits. And since there are d coordinates, it's d log k. And overall communication cost is n d log k. You can analyze this result. And the result looks very similar to binary quantization. But with a difference, the denominator in mean square error has now k minus 1 square term. Meaning if you quantize into more and more bins, the mean square error goes down further and further, which is very expected. And again, if you assume that all the vectors have unique norm, then if you have d log k bits per client, then the mean square error goes down as d divided by nk square. Okay. So let's say you want a mean square error of now order 1 by n. Then k should be square root d. So number of bits would be d log d, roughly. Okay. Do these schemes make sense?
Yep.
Okay.
Do you know, did you test how? I'm just wondering how would this affect if you put it inside an SGD? Do you know how this affect the convergence?
I have some plots later. I will show it to you.
Okay.
Yeah, I have some simple plots. Yes, I will show it to you. Okay. But we felt d log d bits is too much, so we wanted to improve it. So I'm going to talk about two improvements. The first one uses random matrices, and the second one uses arithmetic coding. So let's start with random matrices. So notice that, let's say you quantize a value between minimum and maximum. The error you incur per coordinate is roughly x max minus x min, or x max minus x min by 2, however you think of it. So if your vector has a small difference between minimum and maximum, then your compression would be much better. So what we thought was, if you randomly rotate this vector.
Anand, I have a question. So you may have mentioned this, and I maybe didn't pay attention. But when you quantize, how bad is it just to quantize to round up or round down the value instead of doing it probabilistically?
That's an amazing question. It's a really good question. I should have had it in the slides. It's a really good question. Thank you. So notice that, consider a special case where all the values are at the middle. Not middle, like let's say they're all at 3 by 4.
Okay.
And the minimum is 0, maximum is 1. Okay, the x min is 0, x max is 1, and the values are all 3 by 4.
Yeah.
So you incur an error of 1/4 per coordinate per client.
Yep.
And when you sum them up, they don't cancel each other. So your mean square error now doesn't go to 0 as a function of n.
Okay.
So this is the advantage, because it has a constant bias. The bias doesn't cancel out.
And the other scheme, if you just do it probabilistically, then
they cancel out, because think of it this way: you have a set of, let's look at x hat, right? It's a sum of n random variables.
Yeah.
So in expectation, now we have no error.
Yeah.
But when you compute the variance of an average of n random variables, the variance goes down as 1/n.
Yeah.
So that's why we gain, and our mean square error goes to 0 if you have more and more clients.
Okay.
But if you do like without probabilistically, then you always incur a constant error.
Oh, so you're saying the estimator would be biased?
It could be biased, because imagine minimum is 0, maximum is 1.
Sure.
And
Yeah.
all the values are 3 by 4. You will incur an error bias, right?
Yeah.
Yeah.
All right. Thanks.
Yeah, that's a great question, because that's the first thing someone was doing before we started this project.
Oh, okay.
Yeah, that's a very good question. Thank you. So since the key observation here is it's unbiased, and that's why the mean square error goes to 0 as a function of n. If you do k levels, again, it goes to 0 as a function of n, but with a much faster rate, d divided by nk square. But as you can notice, if you have more levels, the effect of bias will decrease also. I hope that makes it more clear, because if you have k levels, then the effect of bias will be roughly maximum minus minimum divided by k. Yeah. So previously, people used to use a high value of k, but round it off. But we said you should do stochastically, so things cancel out each other.
Okay.
Thank you. So going back, we said the error is roughly maximum minus minimum. So smaller these values, the smaller the error. So what we decided was, we randomly rotate the vector. When you do a random rotation, you can prove that the difference between maximum and minimum is roughly of the order of square root of log d by d times the L2 norm of the vector. So we can definitely use it to our advantage. And the way we do it is, for each client, the client first rotates the vector with a random matrix R. And then it quantizes each of the coordinates of this vector zi into k levels and gets a vector yi. It removes the effect of quantization. So, sorry, please.
Yeah, we lost the video. We can hear you, but we can't see the slides.
Oh, I am not sure. Let me see. Should I reconnect? Just give me like.
Probably, yeah. Yeah, maybe reconnect.
Okay. Do you see me?
Yeah.
Yes.
Okay.
Yeah. Now it's better. Yes.
Okay. I'm inside a Google office, so I don't know why.
And we're using Google Hangouts, so.
Okay. Can you see the slides?
Yes. Yeah. Yes.
Okay. So just to reiterate, each of the clients multiply a vector with a random matrix R and then quantizes them. And the server takes the average of these quantized vectors and then applies an inverse rotation. And our intuition is that it reduces the minimum and the maximum value, the difference between minimum and maximum values. So this X hat bar is a better estimate. First, observe that even here you're doing a k levels of quantization, so it doesn't change the communication cost. You still need to send log k bits per coordinate. But the mean square error now goes down from d divided by nk square to log d divided by n times k minus 1 square. So the change is in the numerator, which went from d, number of dimensions, to logarithm in the number of dimensions. This is a very big savings. But the catch with this algorithm is that if you want to rotate a high dimensional vector, it takes time d square, which is very slow if you want to do it in a phone. But luckily for us, people know efficient ways of doing random rotation. And we borrow some results, which was introduced by Nir Elian et al. In the context of Johnson-Lincoln's cross transforms, where we use a product of Walsh-Hadamard matrix and a diagonal matrix. So our random matrix is H, which is a fixed Walsh-Hadamard matrix, and D, which is a diagonal matrix where each diagonal entry is either plus minus 1 with probability half. So now multiplying with D takes time only linear in a number of dimensions. But multiplying with H can be done very, very fast using Fourier transform. So the time complexity of this algorithm is number of dimensions times log of number of dimensions. The second improvement, which we thought was, instead of using random rotation, we might be able to do something which people in information theory teach in class 101, which is arithmetic coding or Huffman coding. So what's the key idea? All the previous schemes which I described before used fixed log k bits for each dimensions. But there's no need that you need to use log k bits for each dimensions. For example, let's say a particular Bing number 5, appears a lot. Then you can use very few bits for that. And if a particular Bing appears very less frequently, you use fewer number of bits, more number of bits. But we don't know how many times each Bing appears. So what we first do is we describe a quantized distribution. And then we encode using arithmetic coding corresponding to the quantized distribution. This is like the simplest universal scheme, compression scheme you can think, which is describe the empirical distribution and encode using the empirical distribution. Turns out this works very well. Recall that previously we needed d times log k, but this number improves to 1 plus log of k square by d plus 1. If you scale this equation for a bit, you realize that if you choose k equals square root of d, then the number of bits would be just order d per client. So the total number of bits is n times d. But the mean square error now goes to 1 over n. Okay? And it's a very simple, nice proof. we use the fact that these vectors have some fixed unit norm before quantization and show that the entropy of such vectors is small, entropy of such discretized vectors is small, and use it to bound the communication cost.
I have a question. So how do so each client will generate a random rotation matrix R, and then how does the master or the aggregator is undoing these rotations? I may have missed this.
Sorry, that's a good question. So let me go back. So the matrix R is same for all the clients.
And how do they agree on this R then?
We assume that the server and the clients have a source of public randomness.
Oh, okay. Okay.
Yeah.
Okay.
Yeah. In practice, people just use like a random seed and use a pseudo-random generator.
Okay.
But if you don't have a public randomness, you can simulate it using roughly logarithm in the number of parameters you have.
Okay.
Yeah. So this is for random rotation. But for the variable length coding, you don't need any random rotation. You just quantize your vectors individually.
Yeah.
And then you just count how many times each being used and use the arithmetic coding corresponding to that scheme.
Yeah.
It's very clean, yeah. What was surprising to us is this variable length coding scheme is in fact minimax optimal. But notice that this gives just one point. I just described you a scheme where for a communication cost given as square root d, it gives a mean square error of 1/n. But if you want a knob to vary the communication cost versus mean square error, we just say, instead of asking all the clients to send their information, ask randomly selected alpha fraction of the clients. So this will give you a nice trade-off between mean square error and communication complexity. Turns out this is optimal. The lower bound results follows from results from a paper by Zhang et al. In NIPS 2013. But what we show is the mean square error scales inversely proportional to the communication cost. Or a different way of looking at it, which I like, is product of communication cost and mean square error scales linearly in the number of dimensions. And this is information theoretically optimal for all possible schemes. Okay. Any questions?
So far, so good.
All right, thank you.
Again, on my side, so I don't know if other people have questions. They can feel free to ask.
Okay, all right, sure. Let me continue. So this was our communication complexity result, and we now know that it cannot be further improved because it's minimax optimal. So let's see some experiments. Here is a first experiment where we ran a k-means algorithm. Here the goal is you're given an image data set MNIST, and you want to cluster it into 10 clusters. On the left side figure, I'm plotting the k-means objective as a function of number of iterations. Notice that for a given number of iterations, the no compression schemes works the best, which is obvious because if you, for a fixed number of communication rounds, you want to send as much information as possible at each round. But if you plot the objective as a function of communication cost, the variable encoding performs the best because it has a mean square error of 1/n. Rotated works slightly worse because it's a log d by n. Stochastic k level gives you d divided by n, and it's slightly worse. And no compression is way off. We repeat the same exercise for PCA, where we want to compute the topmost eigenvalue. Again, the order is no compression works very badly. Uniform compression works okay, rotation improves, and variable length improves it even further. And going back to the question which someone asked about SGD, here is an image classification data set, which we use to train. This is a CFAR data set. It has 50K images, and number of dimensions is roughly 1 million. And we divided this data on 100 clients with 500 samples each, and we ran an SGD. Again, notice that if you plot with the communication round, the test set accuracy of the no compression is the best. But if you plot it as a function of total amount of uplink communication cost, the rotated quantization works better than k-level quantization, and both of them are far better than the uncompressed version. Does this answer your earlier question?
Yeah. I have a question about the no compression. So you should it be constant? So
what do you mean by should it be constant?
So you're using 32. I mean, for me, no compression is infinite number of bits. But I mean, are you using like a 32-bit?
A good question. This is using 32, I believe. Yes.
Okay.
Yeah. I think you can argue that if you go after like 3 log d bits, 3 log d by epsilon bits, then the error in your representation will be roughly epsilon.
Okay.
Yeah. So the takeaway message for communication is we looked at 3 schemes.
Can you go back to the last slide?
Yeah.
So for the second picture, it seems that for the no compression, your test accuracy can go to, can be better than the other 2 schemes.
Oh, it's again a very good point. If you remember, the mean square error was sigma divided by root t.
Okay.
Where sigma is like the mean square error in your gradients. So when you compress them, you hit a higher bottleneck. When you compress them, the mean square error increases, obviously. So you always you cannot hit the same accuracy as the no compression scheme. So the way we use it is initially we train it with a compressed scheme. So you kind of go with fewer number of bits, we go to a very high accuracy. And once it plateaus, you start the no compression scheme and try to go further up.
Okay, thanks. And why is the rotated one like better than the stochastic level one?
Because of this result, which we showed that the rotated result has a smaller mean square error compared to the stochastic K level.
Okay.
Yeah, and this difference is roughly, theoretically, it's somewhere difference between D and log D, but in practice, it's difference of, for example, in this case, it gives you like a 0.5 improvement.
But which one achieves the information theoretic limit? It's not the rotation, right? If I understand it correctly.
Yes, it's a variable length coding. It gives you 1/n. But I think when we generated these figures, we didn't have that. So
okay.
Yeah. Yeah.
Okay.
But I believe in this case, it works very close to the rotated quantization.
Okay. Which one is more practical? Whatever practical is. So.
That's a very excellent question. So if I talk about the privacy, I can answer the question more.
Okay.
If you don't have privacy constraints, variable length is more practical. But if you have privacy, variable length might not be feasible. I'll explain in a second. Okay, I have 10 minutes, so maybe I'll rush a bit. So we look at privacy in the lens of differential privacy. Roughly speaking, each client sends some kind of a compressed or quantized vector, and the server estimates the mean by some function as before. So the notion of differential privacy gives you plausible deniability, meaning if you given 2 data sets, just by looking at the output, someone cannot differentiate between if a particular user was used or not. So let's see the more mathematical version. So let's say you have 2 data sets, x1 to xn, and another data set, x1 to xn, where the last value is changed to xn prime. We say an algorithm is epsilon delta differential private if the average, which we computed, which is x bar hat, the probability of it being in any set differs at most by e to the epsilon and an additive factor delta. If you haven't seen this before, it takes some time to digest it, but roughly speaking, no one can identify a single user xi based on observing a mean. Okay. I saw someone had given differential privacy talk like a couple of weeks ago, so I'm hoping this will be familiar to many of you. So, okay, so what's the most standard way of computing this? The server computes the average as before using the compressed schemes, and then you just add some Gaussian noise or Laplace noise or whatever noise you decide. And usually the noise scales as 1/n epsilon times log 1/delta. I would like to note at this point, the privacy guarantee we are looking for is what is called global differential privacy, where x bar hat is differentially private. So it turns out you can easily show that this model is epsilon delta differentially private, but there are some issues. The server may be negligent and it may forget to add the noise. So the users need to crush the server. The server will add the noise before they release the model to public. And the second issue, which is like a big, is privacy, which is the server will learn the true X hat. This means the server has the true value of the mean, so maybe it can infer something about the users. So we propose a slightly different scheme, which is each of the servers, clients, will add a little bit of noise, and the server just computes the average of them. So what's the advantage? So notice that each of the clients are adding a small amount of Gaussian noise. So the total noise you added is also a Gaussian. And if you do the math, the total amount of noise added in this scheme is same as the noise added in the previous Gaussian mechanism, which is sigma square. So the model you learn is epsilon delta differentially private. So let's call the previous scheme server Gaussian mechanism and the current one distributed Gaussian mechanism. This mechanism is very useful in two scenarios. The first one is server is negligent but not malicious, meaning the server doesn't care to learn the average, but it may forget to add the noise, or for some issue it didn't. In this case, as long as the server just finds the sum, when you release the model is differentially private and people cannot learn about an individual user. The second case is the clients do not trust the server. Here, you can implement this along with a secure aggregation scheme, which is some kind of a homomorphic encryption, to ensure that the server learns only X hat, meaning the server only gets the sum but not the individual values. In this case, even though you guarantee a global differential privacy, the server will not learn anything about individual users. So going back to one of the questions before, why is which one is more practical? Turns out to do the secure aggregation, you need to have you cannot use variable length coding. The way that scheme is designed, you need to have fixed number of bits per location, per dimension. But if you just want very good communication efficiency, variable length coding is more practical. Okay. But turns out this algorithm is not communication efficient because at each client, they compress the vector and then they add Gaussian noise. So it's no longer compressed, it's a real value. So you lose all the benefits of the quantization. And the second disadvantage is the cryptographic scheme operates over some discrete values or some finite field. So if you make it Gaussian, you cannot use the cryptographic scheme again. Any questions? Okay.
No, not on my side.
Okay. So because of this, we prefer to use the rotated quantization as opposed to variable length scheme. So one obvious way of circumventing this, going back to real values, is you first add the Gaussian noise and then you quantize it. And the server computes the average by taking the average of these quantized Gaussian vectors. Turns out it's not clear why this is differentially private, because sum of quantized Gaussians is not a Gaussian. So what you get might not be a Gaussian distribution. So you need an additional proof to show that this is epsilon delta differentially private. And we tried it, it was very hard. And even though we got some kind of proof, it wasn't optimal in terms of constants. So what we proposed to do was to add binomial noise. Recall that we are quantizing the values to one of k values. So what we said is you quantize it to one of k values and you add a binomial random variable. This has several advantages. Firstly, binomial random variables are bounded. So before, if you wanted log k bits per dimension per client, now the number of bits is log of m plus k, where k is the number of levels of quantization and m is your binomial random variable value. And secondly, the sum of binomials is also binomial. So if you analyze the binomial mechanism as a whole, it also immediately gives results to the distributed binomial mechanism. And finally, by central limit theorem, binomial distribution kind of looks like a Gaussian distribution. So we should be able to recover similar guarantees for binomial mechanism without losing a communication cost, communication efficiency. So here are our results. The Gaussian mechanism was very well known. What we showed was that the binomial mechanism is also epsilon delta differentially private. And the amount of noise you need to add depends on all of L1, L2, and L infinity sensitivity. But the dependence on L1 and L infinity goes to 0 as a function of variance much faster than 1 over sigma. So in the high privacy regime, where you add a lot of noise, sigma goes to infinity, and the performance of binomial and Gaussian mechanism are exactly the same up to constants. And we use this along with the rotated quantization scheme, and we were able to show that if the number of clients and number of dimensions are same, roughly on the same order, the number of bits you need per coordinate is log of nd by epsilon delta. Recall that I was telling you earlier, if you want to send a vector to constant accuracy, you need log t bits. So this is an improvement because we are going from log to log. But we don't know whether this is necessary, and it's possible there are better algorithms to achieve this. So I'll conclude the talk by saying that we looked at the problem of distributed SGD and reduced it to the problem of distributed mean estimation. We gave a minimax optimal scheme for mean estimation, and we also showed how to get communication efficient differential privacy by binomial mechanism. There are several future directions or open problems. The first one is, if you look at stochastic gradient descent, there is some correlation between gradients over time, because between any two time instances, the value of your variable doesn't change a lot. Is there a very principled way of exploiting this to get better communication efficiency? Again, we are looking at, for privacy, we are looking at privacy of a single step. Is there a better way to get better privacy guarantees by studying SGD as a whole? Finally, for mean estimation, we just looked at a minimax rate. It would be more interesting to use some properties of the current instance. For example, maybe we can do much better if the gradients are sparse. So if there is some kind of competitive or instance optimal results, that would be much more interesting. And that's it. Thank you.
Yeah, thanks. So thanks a lot for the very good talk. So if anyone has questions, so that's the time to ask. Yeah, I think Aaron has questions.
Oh, yes, I enjoyed the talk. On the communication complexity part, so you have many users, right? Each user is randomizing its response, if you will, right? It's quantizing randomly. Yeah. Is it possible to correlate the quantization errors across the users so that they kind of cancel and then give you a lower overall variance? Like if the mean was, if the true value was a half, rather than having each user flip a coin to decide whether to send 0 or 1, if hypothetically half the users sent 1 and half sent 0, then it'd be better, right? So I wonder if there's some way of achieving that.
That's a great question. We haven't talked about it. No, that's a very good point. You're saying instead of doing like roughly half of them going right or left, why not exactly half of them go right, exactly half of them go left, so you get 0 error?
Yeah, of course. I mean, it's more complicated, of course, than the example I mentioned. I mean, the true thing is not a half. I guess the different users actually observe different values, right? They all have a different X.
I agree, yeah.
I'm trying to be clear, but somehow, I mean, rather than having them all just use private randomness and just each doing an unbiased thing, individual users could send a biased estimate. As long as the biases cancel out over the course of overall the users, then you're okay.
I would be very interested, but I don't have an answer to this. But I think the lower bounds in the paper which we used actually assume that there is some public randomness. So I don't know how to improve on this lower bound.
It might improve just the constants that are suppressed in the data.
That might be possible. Even then, that would be interesting. That's a good point.
So on the topic of the lower bound, so there's a result in quantization theory, I guess you call it, that says that for i.e. Gaussian sources, the optimum thing if you're trying to do compression is to do vector quantization, right? You take like a long string of X symbols and then compress them all at once. You can keep the Gaussian rate distortion function and so on there. But a simple scheme that does quite well is to just do a uniform quantizer for each source and then do variable length compression. And so that gets within, like, I think it's a quarter bit of the rate distortion bound for every distortion level. I wonder if that is, you know, if that result is related in any way to this, in particular the Zhang-Nips paper. How do they prove the lower bound? Are they doing something similar to that result from rate distortion theory?
That's a good point. I'm not sure. You cannot estimate the mean better than some accuracy.
Your answer. Can you repeat it?
The lower bound which we use, can you hear me?
Yes, now we can.
Yes, sorry. I had to change rooms because it's exactly 2 o'clock. So the lower bound, I think the lower bound we use essentially says that if you have a product distribution over 0, 1 to the D, and you're trying to estimate the mean of this distribution, given public randomness and private randomness, the mean square error follows this equation, which is number of dimensions divided by communication cost. They don't really look at any vector quantization schemes and so on. It's just a Fanos inequality type of lower bound. Can you repeat your question once?
Well, I think I have the answer. I mean, there was a result in rate distortion theory pertaining to a simple scheme that compresses Gaussian random variables quite well, and it doesn't use vector quantization. It just uses a scalar uniform quantizer followed by lossless compression of the quantized values. And that's kind of within a bounded multiplicative loss, you know, of the optimum thing, even when you compare it against schemes that do vector quantization. So this result has a bit of a flavor to that, like, you know, you're just doing like a uniform quantizer with like lossless variable length compression on top of that, and it's like minimax optimal. I just wonder if there's some connection there. That's all.
Yeah, I'm not sure. And actually, I would probably ping you later. I would like to see this paper or this result. Yeah.
Sounds good.
Okay. Thank you.
Any more questions? Do you have to go, Anand?
No, I have time. I changed gear.
I have a quick question. So, I mean, I think in this channel, so I think we had some talks about some variation on SGD that actually use, they add noise to get out of some local minima. Like the Langevin, I think it's called, Stochastic Langevin. So do you know if people studied this trade-off? Because that noise could also be used for privacy and for optimization at the same time.
No, I'm not aware of it, but it's a very good point. Usually, the folk knowledge is the SGD helps you escape local minima, but I'm not sure how much we can buy it, because there are recent papers which say something like all local minima are global minima for neural networks. So
is it true? I don't know.
People know this for example, linear networks without any activations.
Probably because it's convex. But yeah.
No. It's convex if you have just a single linear layer.
Okay.
But imagine it's a product of matrices A1, A2, A3. It's not convex in individual matrices A1, A2. It's not jointly convex in A1, A2, A3.
But still, the local minima is the global minima.
Yes. All local minima are global minima.
Okay, so if no one has questions, thank you again, everyone, for coming and joining the talk. And thanks a lot, Anand, for giving this great talk. Thank you.
Thank you. Thanks for having me.